We're going to be talking about Hardy Weinberg Equilibrium. It helps us figure out the ratio of carriers that are in a population for specific types of diseases. And so these types of diseases are called autosomal recessive diseases. Now what this means is if we had two parents who were both carriers for a disease and they were to have a kid, we're going to get these following genotypes coming out of it. So we're going to have big A, little a, and then little a. So basically this little a is that child that ends up getting two bad copies, two bad alleles for a gene that ends up leading to some kind of disease. And so that is what autosomal recessive means here in this little diagram. Now, the key thing before you get too deep into looking at equations with Hardy Weinberg Equilibrium is knowing what assumptions are being made. What this is to say is that you're not going to have close relatives mating. This is also known as inbreeding or incest because that will affect the available gene pool and that will skew your data. It's also assuming that we don't have selection pressure against the disease. We're also assuming we've got a large population. We're assuming that we don't have genes coming in and out of our populations. And in addition to that, we're assuming that there's no mutations. So these are key things to make note of before you start doing this, and before you go to somebody and say, like, I know how many carriers are in my population. You need to also say that, based on these assumptions, this is when I can say this. And so we're going to walk through a practice problem, and it'll actually let us see the actual equations, in which if we know that 4% of people in our population have some autosomal recessive disease and it's following the Hardy Weinberg Equilibrium assumptions, we can ask the question, what ratio of people are carriers for this disease? And so the very first equation that you look at with Hardy Weinberg is the following. So we've got p squared plus 2pq plus q squared equals 1. And so what this is really talking about are things called genotype frequencies. And so what this really means, if we stick to this example up here, is it's the ratio of AA, of big A, and of little a. So these are also known as the homozygous dominant, heterozygous, and then homozygous recessive frequencies. So that's what this equation is talking about. And then we've also got this other one, which is P plus Q equals 1. And this is just telling us the allelic frequencies. And this is pretty self-explanatory. It literally means that, if you have 70% of your alleles or flavors of a gene are of one type, then 30% must be of the other type. And this is assuming that there's only two versions of a particular gene or alleles for that gene. And so how can we look at this data? So what 4% tells us is what Q squared is equal to. So basically, if we know that 4% of our population has this autosomal recessive disease, what we can say is 0.04 is equal to Q squared. And if we square root both sides here, we'll note how this is equal to 0.2, which is equal to Q. And so based on this tells us right now that we now know what our allelic frequency of our recessive allele, little a, is. And so with this, we can just very simply say that P must be equal to 1 minus Q, which is equal to 1 minus 0.2, which is equal to 0.8. So this tells us that our dominant allele frequency is 0.8, our recessive allele frequency is 0.2, and now what we can do is ask the question, what percentage of people in our population are carriers for this disease? And the carriers for disease are going to be these heterozygous individuals, the people who have big A, little a. And so what this is equal to, so just to spell this out, carriers for disease are people with that big A, little a genotype, and this is equal to 2pq, which is equal to 2 times 0.8 times 0.2, and if you do the math here, 0.8 times 0.2 is 0.16 times 2 is equal to 0.32. Sorry, that's off the board. But basically, what comes out of this is we can now say that 32% of our population are carriers for this disease. Now, this is the key point to take home. You can also ask other questions here, but I think the percentage of carriers in your population is usually the most interesting thing that people want to know. The other thing is like, what percentage of your population are people who are homozygous dominant for this? And you can readily just plug in these numbers with these equations. So we know 2pq was 0.32. We knew q squared was equal to 4%. So 0.32 plus 0.04 would equal 0.36. And you do 1 minus that to get that ratio. And so that's how we can use Hardy Weinberg equilibrium to determine things like this. So I'm going to wrap things up with that. Hope this video helps. Thank you all for watching, and I'll talk to you guys next time.